All right, guys, so we are going to take a look at our last topic for this unit, which is the common ion effect. So, a common ion is exactly what it sounds like. It's chemicals that have one of their ions in common with each other. So, the common ion effect occurs when a reaction or solution at equilibrium has a chemical added to it with an ion that is common to one already present in the solution. Okay, so this addition of an ion shifts the equilibrium as predicted by Le Chatelier's principle to return the reaction or solution to equilibrium. We will still use the methods previously learned, such as equilibrium expressions and Rice tables, to determine the effect of the common ion on equilibrium. So let me give you an example. So if I had a beaker and I had in it a sodium chloride solution that I made, okay? Well, actually, let's use something. I believe let's use iron chloride. Just because something that's a little less soluble. Okay, so we add the iron chloride. I add excess, or I add enough. I make my saturated solution of it. So in this, I have iron ions and I have chlorine ions. Okay. Now, once I've established my equilibrium, I come by and I dump another chemical in. I add a whole bunch of sodium chloride, or add a certain amount of sodium chloride to my chemical that's already there. So really what I'm adding is sodium ion and chlorine ion. Well, one of those, since they are already present, is going to affect this equilibrium that exists. Since chlorine is in common between the two, that is our common ion. And so I'm really adding more chlorine to my equilibrium. And we're going to see, well, what does that do to my equilibrium? Well, we've seen with Le Chatelier's principle, if we add more of a chemical, it shifts it towards the opposite side. So it's going to cause some of our ions to precipitate back into their solid and shift that equilibrium. Okay, so what we want to be able to do is figure out, well, how much of these chemicals do I have once that occurs, once this shift occurs, when it reestablishes equilibrium, what's our amounts of chemicals? Okay, so here's an example. A solution is formed by dissolving iron hydroxide in water to create an equilibrium below. So we've got our equilibrium reaction written. Then 0.10 molar NaOH is added to the reaction. Okay, what is the concentration of each ion at equilibrium? So we're really just solving for this line. That's our goal, is those amounts at equilibrium. Okay, so we can use a Rice table to help us solve this. So initially we've already established an equilibrium for iron hydroxide. Okay, so when we're looking at a question like this, we're going to have two chemicals. All right, when it says then one other one is added, that's the one we're going to just be adding in our change line. The one that's already established the equilibrium, the solution's already made, that's the one that's going to be our reaction that we have. Okay, so I've got kind of a guide over here that goes through the question. So initially the chemicals are already at equilibrium. Okay, so we've already placed this in, right? We already had the solution, it's already at equilibrium. So first thing, I'm going to cross out my solid. Solids aren't in our equilibrium expression. So whatever that equilibrium is that is established, it already had amounts of these chemicals. Now we don't know what those amounts are, so we're going to put X and 2X. Actually, hold on a second. We're going to put S instead of X because we're going to be looking at molar solubility as well. So let me actually erase that. Minor change here. We're going to put S and 2S. Just like our last unit where we're looking, because this is the solubility of a chemical, we got KSP, so we'll use S as a reminder of that. Now, whatever that equilibrium is, we've already got some of our chemical in there. Then we come by and we dump the 0.1 molar NaOH in. Well, we want to think about what is in common. What is the same between these two chemicals? Well, this is really adding sodium ion and hydroxide ion. Okay, the hydroxide is really what we're adding here. Okay, that's going to affect our equilibrium. The sodium will have no effect on our equilibrium because it's not present in this reaction. So we're adding 0.01 molar hydroxide, right? So since this is a 1-to-1 ratio, we're going to get that much hydroxide. So 0.010 molar hydroxide is added to the reaction. So I'm going to add it under my hydroxide line. Okay. Now, are we adding any iron to this? No. So I'm not going to add anything there. Okay, so this is what we're physically doing. This one's a little bit different in that we're starting with an amount we don't know, and then we are adding what we do know to the solution. Okay, and then we bring these down. We've got S, 2S plus 0.010. Okay, so we got our equilibrium line. Well, we still need to solve for S on this line. Okay, now to solve for S and our new equilibrium concentrations, we have to use the equilibrium expression and solve. Remember, your equilibrium constant will not change. This value is going to stay the same. We've got that value. So I'm going to write my expression. We've got products over reactants, but our reactant is a solid, so we leave it out. So there's our equilibrium expression. Now, here's the little trick we get to do. Before we plug these in, we're going to make a little assumption. So it says, due to the nature of the problem, we would end up needing a quadratic formula to solve this. And they have taken the quadratic formula off the AP exam. So what do we do to solve? Well, there's a little assumption we can make, okay? A little side kind of thing we can do. Since our KSP value is really small, it's less than a 10 to the minus 3, because we got 10 to the negative 16. That is a very small number. Let's see what that number looks like. 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 7, 9. Okay, really small number. Crazy small. So that's meaning that this is favoring reactants. This chemical barely dissolves at all. Okay, so we dump a whole bunch in, and you're going to get a couple little ions that actually separate and dissolve. So very little of this iron hydroxide dissolves. So these amounts for S are going to be very, very tiny. Whatever they are, they're very small. Now, if I have a very, very tiny number and I add 0.01 to it, I'm basically going to round to my sig figs, and I'm going to have this number. Okay? So, and we're going to see that later and prove this. So we're going to take this term where we've got something plus this value. We're going to say this pretty much equals 0.010. That this number is, we're betting, right? We're betting that this number is so much bigger than this that this part doesn't matter. Okay? And it's because our equilibrium lies so much to the reactant side. We barely have anything here. So now we've got easier numbers to deal with. Our KSP is 7.9 times 10 to the negative 16th. My iron is S, I'm going to leave that. My hydroxide is 0.010 squared. Okay, so instead of putting this whole term in for hydroxide, I'm going to put this in. Put that in for iron. Okay. So what do we do now? We can simplify. 7.9 times 10 to the negative 16th equals, if we square this, we get 0.00010 times S. Now we just divide by that to isolate our S. And I got that it equals 7.9 times 10 to the negative 12th. Okay, cool. We've gotten our S value. So this is also the molar solubility of iron hydroxide in this situation. But then it wants the concentration of each at equilibrium. So we report our answer. Concentration of iron 2 plus is equal to S, so 7.9 times 10 to the negative 12 molar. Concentration of OH equals 2 times S, 7.9 times 10 to the negative 12, plus 0.010. Where did I get that information? Right here, right? I'm plugging back in here. So what does that give me? Let's do the math. 2 times 7.9 times 10 to the negative 12 plus 0.010. Hey, look, when I added this number, I got the exact same number out, because with my significant figures, this number is so small that it does not matter. So this also proves that our assumption is true, right? This S value is so tiny that it doesn't affect this. So our assumption here is fine, okay? So whenever we have an exponent there that is super small, less than 10 to the negative third, we can do this, okay? So there's our molarity. All right, so that's what we're basically doing here. We are trying to figure out what happens when we dump another chemical in. How does the Le Chatelier's principle thing actually work? Okay, so it says values, based on the values and Le Chatelier's principle, we can see that the equilibrium shifts left due to the addition of the common hydroxide ion. So we're getting an addition of that hydroxide, so we're going to shift that to the left. We're going to reduce this amount, use up some of the iron and shift it to the left. Okay, let's take a look at another example. So calculate the molar solubility of CaF2. So we're looking for S in a solution where 0.25 molar CaCl2 is added. Okay, so this is the chemical that's being added. This is the chemical that we want the reaction for. Okay, this is the molar solubility we're looking for. So it also gives us, it says the solubility product constant of CaF2 is this. So that's our KSP. Okay, so the one we have the KSP for is the one we want to write the chemical reaction for. So it's a solid, because we're looking at molar solubility. So we're going to just break it into its two ions. Those are our aqueous ones. All right. Now, RiCe. This is our solid. We're going to get rid of it. Okay, first thing we're going to do is say, okay, this has already reached an equilibrium. We've already got this established. This is some amount, and this is 2 times whatever that amount is. Okay, it's 2 to 1 ratio. Now, we are coming by and we're going to dump this chemical in. Well, what's in common? I have Ca2+, and I have 2Cl-. Ca2+ is what's in common. This chemical, there's one of these made for every one of these chemicals that dissolves, so it's a 1-to-1 ratio. So I'm adding 0.025 calcium to this. So I've got 0.025 plus S, and I've got 2S. All right, so we've got that equilibrium line. We can write our KSP expression always. Calcium 2+, F minus squared, and I can plug it in. Now we're going to make our little assumption. Okay, this is our little star thing we get to do. We're going to say that this is basically equal to 0.025 because this KSP value is so tiny, right? So these numbers are really tiny, so it's not going to affect that value. Okay. 3.9 times 10 to the negative 11 equals, we're going to go ahead and get, let's see, our calcium, we're putting in 0.025. Fluorine, we're putting in 2S, and we're squaring that value. I'm going to simplify. So I'm just going to start with the 2s squared. So 2 squared is 4, s squared is s squared. Now I'm going to multiply this, which gives me 0.10 s squared, because 4 times 0.025 is 0.1. All right. To simplify next, I can divide both sides by 0.10. Bring this over here. So dividing that, I get 3.9 times 10 to the negative 10 on the left and I get S squared on the right. We can square root both sides, and that would give us, so when I square root, if I don't, like, there's two ways you can do it in your calculator. Of course, you can hit the square root button and then type your stuff in, or you can do 3.9 times 10 to the negative 10 and raise it to the 1/2 power. Both of those give you square root. But we should get, let's see, we get 1.97 times 10 to the negative 5. So we get 2 sig figs. So 2.0 times 10 to the negative 5 is S. Okay. We are looking for our molar solubility, so we have answered our question. All right. So this would be the molarity of our chemical CaF2 after we've added this other chemical. Okay, so that's how much molar solubility, remember, is how much of the chemical actually is dissolving, not how much is present in the container total. It's just how much is actually dissolved into our ions. So we throw M on there for molarity. Okay, let's try one more example here. Okay, a solution of silver chromate is made and gives us a KSP, so that's the one we want to write the reaction for. And then this is a solution of silver nitrate is added to it. So that's what we're going to add. And we're looking again for the molar solubility of this, so we're solving for S. So I'm going to start with my reaction, Ag2Cr O4 solid in equilibrium with Ag. There's 2 of those. And then we got CrO4. That's a 2 minus charge, and silver's a positive charge. Okay. All right. Those are our aqueous ones, so we can write that too. Our ICE, we set up our rice table. All right. So I'm going to start with setting up that first line. My initial is those amounts. We don't know what those amounts are. We know it's 2S and S, just that 2-to-1 ratio. Now we're coming by and we're dumping this chemical in. Now let's look at that chemical. We've got silver and we've got nitrate. So we're adding silver into our beaker. We've got 0.035 molar of the whole solution, and it's a 1-to-1 ratio. So I'm adding 0.035 molar to that chemical. I'm not adding anything to the chromate. I don't have anything added there. So now we got 2S plus 0.035. We've got S over here, and this is where we make our assumption that this is basically 0.035 because our KSP is so teeny tiny, 10 to the negative 12. All right, I'm gonna write my KSP over here where I've got some space. All right, I've got Ag plus squared times CrO4 2 minus. I'm going to replace my KSP with my value. 9 times 10 to the negative 12 equals, my silver is coming from here, 0.035, and I am squaring that. And then my chromate is just S. So we can simplify. All right, 0.035 squared gives me, let's see, we've got 2 sig figs, so 0.0012 S divided by that on both sides to isolate my S. 9 times 10 to the negative 12 divided by 0.0012. Ooh, ugly looking number. All right, 7.5 times 10 to the negative 9 is my S value, which is what we're looking for. We're looking for that molar solubility. So there's my concentration of silver chromate after I've dumped in my silver nitrate. Okay, that's how much actually dissolved. We can also check our assumption here if we want. So So we can say, okay, if 2 times 7.5 times 10 to the negative 9 plus 0.035, that gives me, I'm just going to put it in regular notation, 0.035, 0.00015. So see how tiny this is? So this whole thing is basically equal, when we round to sig figs, to 0.035. So this assumption we made is fine. So you can always check that, make sure, like, does that seem right? Yes, it does. Okay, so that's what we're doing here. We are calculating our molar solubility. And then, so some of them might have you do the molar solubility like we did in topic 11, then recalculating when something is added to it, and then looking, did our concentration increase or decrease, what's going on. So it's doing some a little more in depth there, but that's basically what we're doing here, looking at that common ion effect. Okay, so when you're looking at these, first thing, if you have the two chemicals, determining which one gives you the KSP, that's going to be the one we write the chemical reaction for, and our reaction is just that chemical dissolving because it's SP, right, that solubility product. And then the other one is what we're adding, okay, and then these are different because we start with our S values, right? We know there's some sort of equilibrium already, we're adding to it. We're only adding to one of the chemicals, all right? I will let you guys try this out. Have a good day.